Let's then look at the impact of the eddies on the mean circulation. As we said here already, that the radiative forcing gradient is going to be creating instabilities, and we have kind of derived the thermal wind relations by looking at zonal mean meridional structures and saying for a geostrophic balance, if you have a gradient in temperature, you're going to have vertical shear. So geostrophic shear, which gives us a nice westerly jet. Then we are saying the westerly jet can be unstable because of these angular momentum conservation failing, and we have associated eddy momentum and heat fluxes. If they are going to perturb the mean state, then how does the mean state adjust? These are kind of the key questions. Going back to our equations, the zonal momentum equation, the thermodynamic equation. Let's write it in terms of eddies and the mean flow. So we're going to write this equation as the zonal mean, zonal and meridional velocities, and appropriate terms have been neglected, and the meridional gradient of the eddy momentum flux, plus this zonal eddy stress. Let's say if the eddies are running around the zonal mean state, then they're going to create some momentum dissipation, which can be thought of as eddy stress. And similarly, writing the thermodynamic equation, now we can use the vertical scale height and the Brunt-Väisälä relations to look at the vertical term of the thermodynamic equation. Write again in terms of the eddy fluxes in the zonal direction, the meridional divergence of the zonal eddy heat flux. So remember, the eddies are deviations around the zonal mean, and the diabatic heating term and the heat dissipation term or thermal dissipation term that's got an averaged, so it doesn't go away when you averaged in the zonal direction, because the eddies leave a net rectified momentum and thermal damping, if you will. Okay, so n squared has this expression where kappa is again R over Cp. This is the background temperature, scale height. dz of course is our log pressure coordinate. So Fx is zonally average drag, accounting for the unresolved eddy stresses that may exist throughout the domain, and Ft zonal average represent a thermal dissipation occurring in unresolved processes. Okay, within the confines of the quasi-geostrophic approximation, which means you are nearly geostrophic, but there are terms that cause deviations from the geostrophic balance. The zonally averaged meridional momentum equation can be written basically this equation that we looked at. I have to go all the way back, but I won't do that. Can be written as Coriolis term balancing the meridional pressure gradient. So that's our geostrophic balance, which when combined with 10.1 C, which also is not here, produces F0 times du bar dz plus R or G dt dy equals 0. So now we are relating the vertical effect of, let's say, vertical shear of the zonal mean flow with the temperature meridional gradient of the temperature, which is what? This is our thermal wind relation, right? Horizontal gradient of temperature is related to the vertical shear in the geostrophic flow. That's all this is saying. We are still on a beta plane, looking at area that's centered around F0, which is the mean Coriolis for that region that we are looking at. Now using these two, these two equations. In a steady state, we can set these to be 0, which is a strong constraint. Adiabatic, so Q dot goes to 0. Inviscid, so we can set the two eddy momentum and eddy heat stresses dissipations to 0. So this equations then become much more simplified with F0 V equals minus del U star V star or del Y. Did I have that wrong before? No, it's okay. So this is just the deviation of perturbation of the meridional velocity around the zonal wind. Okay, so zonal average, zonal mean, zonal wind is got eddy fluxes which create meridional perturbations. All it is saying is that the meridional divergence of the eddy flux, which creates deviations of the zonal flow, is going to be brought back to equilibrium by the Coriolis, which is acting on the deviation from the zonal. Right? If the zonal mean flow is perturbed by the eddy momentum flux divergence, then you're going to create a meridional component of the velocity, which is then going to have a Coriolis effect acting on it, and that's going to bring the system back towards this geostrophic and thermal wind balance that we are seeking. So this is the idea of having the mean observed structure that is so solid, and yet there are eddy momentum and heat fluxes. So something must be happening to keep this mean structure in near equilibrium in a quasi-geostrophic sense. And that's what this balance is saying. For the heating terms, you have the vertical perturbations of the heat being compensated by the input from eddy heat transport. Okay, so thermal wind balance is going to be affected by meridional eddy heat fluxes, which is going to be compensated by the vertical perturbations of the system by the eddy fluxes. So that's the basic idea. So we will do the other case in the next podcast, because I want you to absorb this idea that baroclinic instabilities are creating these eddy momentum and heat fluxes. The system wants to be in strong geostrophic balance in a thermal wind sense because there is a meridional temperature gradient. Eddy fluxes can perturb this thermal wind balance, but the balances are maintained by Coriolis effect on the meridional perturbation velocity and vertical advection by the perturbation velocity. Okay, I hope it makes sense.